The Haber-Bosch process. The history of the Haber-Bosch process is a story of a country, Germany, its pursuit of power, and the passionate chemist Fritz Haber, who wanted to help Germany achieve that power. It was Fritz Haber's idea that Germany must become independent from imports if they were going to win a war. Through chemistry, he took hydrogen and nitrogen from thin air. This gave Germany a method for producing ammonia with the possibility to make their own munitions and fertilizer. This process only yielded a small amount of ammonia. The industrial chemist Carl Bosch developed the process for large-scale production. Just before World War I, in 1913, Germany was producing ammonia at the rate of 30 metric tons per day. Even though the British Navy stopped shipments of nitrates from South America to Germany during the war, they can continue to produce large numbers of crops to feed their people and make large numbers of munitions. This extended World War I for many years.
Gaseous nitrogen combines with gaseous hydrogen to synthesize gaseous ammonia. Hydrogen is obtained from the reaction of methane and H2O steam. The hydrogen from the reaction reacts with oxygen from the air, producing water and leaving behind nitrogen. Nitrogen and hydrogen are sent to a reactor in a 1 to 3 parts by volume ratio. These gases are then heated at temperatures of 400 to 450 degrees Celsius, giving them more kinetic energy. The gases are then compressed at 200 atmospheres. This is about 200 times greater than the pressures we are subjected to on Earth. An iron catalyst is used to ensure the reaction can be carried out at a lower temperature than otherwise be needed. The iron catalyst does not affect the equilibrium. It only increases the rate at which the equilibrium is reached. The nitrogen triple bond is broken here, which activates the reaction to get the ammonia. Gases are then cooled down and ammonia is liquefied. Unused nitrogen is then returned and recycled back to the reactor. Le Chatelier's principle states that when a system experiences a disturbance or stress due to temperature, pressure, or concentration changes, the system will respond to restore a new equilibrium state. Remember, the Haber-Bosch process is a reversible reaction, but the forward reaction is exothermic, thus releasing heat. So if Fritz Haber adds more heat to the reaction, the equilibrium will shift back to the left to produce more hydrogen and nitrogen. Using a lower temperature in the process slows the reaction but increases ammonia yields. High pressures increase yields as well. In order to speed this process up, they lower the temperature to 400 to 450 degrees Celsius while increasing the pressure to 200 atmospheres. It is also extremely expensive to build a factory that can withstand high temperatures of this stature, thus enforcing the compromised temperature.
The Haber-Bosch process has resulted in many modern-day applications that have advanced society in a relatively short period of time. Ammonia is used as a product in pharmaceuticals and household products, fertilizers, and explosives. Most ammonia, about 80% as of 2014, is used in fertilizers. Nitrogen fertilizer is one of the most common ones because nitrogen is one of the most important micronutrients that plants need in order to grow. Nitrogen from urea, anhydrous ammonia, and ammonium nitrate are some of the most common fertilizers used. Many explosives use ammonium nitrate. Ammonium nitrate comes from a reaction from nitric acid and ammonia. The nitric acid, by the way, is also produced partially using the Haber-Bosch process. They use nitration, which is the addition of nitrogen to organic compounds. It serves as a basis for many common explosives such as TNT and nitroglycerin, among others. Ammonium hydroxide is also used for common cleaners in everyday life. Dilute ammonia, typically with concentrations less than 3%, used commercially, is used. And ammonia as a base turns the fats into soap, which the water in the solution can then dissolve. What's left is the ammonium hydroxide, which then evaporates. Approximately half the protein in today's humans originates with nitrogen through the Haber-Bosch process. And the Haber-Bosch process now produces 450 million tons of nitrogen fertilizer per year. And about 3 to 5% of the world's natural gas supply is consumed in the Haber-Bosch process. And when combined with pesticides, thanks to this process, agricultural productivity has quadrupled over the course of the 20th century.
As with all good things, there has to be some downside. And that comes in if you've ever come across a pond or lake with a layer of green goo floating on the top and found yourself wondering what that was. That's eutrophication, which occurs when excess nitrogen is introduced into the environment, enabling unprecedented growth of algae, green goo. For the same reason that the Haber process and ammonia are so great for our crops and human growth, it is bad for our ecosystems. 50% of the nitrogen from our fertilizers is not assimilated by plants, meaning that it is found as a volatile chemical compound in our environment. Without being absorbed by the intended recipient, the crops, the ammonia infiltrates our water supply. In our ponds and lakes, this negatively impacts the ecosystem and decimates the food chain.
The Haber-Bosch process is one of the most revolutionary inventions that changed our world. The process of synthesizing ammonia involves nitrogen to combine with hydrogen. It has contributed to many modern-day applications and has advanced our society.